very much. Thanks for the invitation as well. So today I'm going to be talking about a collection of papers that I've written with my colleagues as well. And it's about a method called synthetic likelihood, and it seems that this method is quite useful for extending simulation-based Bayesian inference into higher dimensions. So I just want to give a special mention to Leah and Zawen, who are my PhD students, and also Victor, who is David Knott's former postdoc. So they've actually done most of the hard work for these papers. Okay, so let me just first talk about a bit of the background. So in Bayesian statistics, we're interested in sampling from the posterior distribution, which is proportional to the likelihood times the prior. Now, unfortunately, we can't generally perfectly sample from the posterior, so we need some other kind of approach. And one of the most popular methods for sampling from distributions that you can't sample from perfectly is this method called Markov chain Monte Carlo. And the idea with these MCMC methods is to construct a Markov chain such that the limiting distribution of the Markov chain is given by the posterior. Now, one of the most popular implementations of MCMC is this Metropolis-Hastings algorithm. Okay, so let's just pretend that the current value of the Markov chain is given by theta. We propose to go to a new value theta star according to this proposal distribution, and this is something that the user has to specify. And then the theta star becomes the next value of the Markov chain according to this probability here. And then, of course, with a probability of 1 minus that, then the next value of the Markov chain is just going to be given by the current value of the Markov chain. Now, for a large class of models that scientists are interested in these days, the likelihood function can be very computationally expensive, and it can even be computationally intractable. So you notice that in this Metropolis-Hastings ratio, we need to compute these likelihoods here. So if our likelihood function is very expensive to calculate, then we can't really use standard MCMC methods in order to sample from the posterior. Now, it turns out that even if we can't compute the likelihood function, if we're able to generate simulations from the model, then we can actually use these simulations in order to estimate that likelihood. And the most popular simulation-based Bayesian method is something called Approximate Bayesian computation. Okay, so the idea of ABC is actually really straightforward. You generate a whole bunch of parameter values, and then conditional on each of those parameter values, you generate a data set, and you compare that simulated data set with the observed data set. Now, effectively what you do is you keep the values of the parameters that generate simulated data that's somehow close to the observed data. Now, for reasons that will become clear later, typically ABC does this closeness assessment on the basis of some carefully chosen summary statistics. So in ABC, what we actually do is we target not the posterior conditional on the observed data, but the posterior conditional on the observed value of the summary statistic. Now, this in itself is not particularly useful because if the original likelihood function is intractable, then this summary statistic likelihood is also going to be intractable. But it turns out that we can estimate this by simulation. And effectively what ABC does is it gives you like a non-parametric estimator of this likelihood. Now, because the ABC is effectively a non-parametric method, which I'll talk about more on the next slide, then the choice of the summary statistic is quite crucial. Okay, so it's going to be a trade-off between information loss and also dimensionality. Okay, so the higher the dimension of the summary statistic, the less information that we're going to be losing when going down from the full data set down to our summary statistics, which is good. But then the bad thing is that ABC is not particularly well equipped to deal with high dimensional summaries. So in the context of ABC, we want a low dimensional summary statistic that's still quite informative. Okay, so this is the way that ABC goes about estimating the likelihood. Okay, so we have some proposed value theta, and then we simulate n independent data sets from the model. And then for each of those individual data sets, we compute the corresponding summary statistics. And then effectively, we estimate this intractable likelihood of the summary statistic with this term over here. And then what we basically do is we can plug this estimator here straight into, for example, this Metropolis-Hastings ratio, and that will give you something called an MC-MC-ABC algorithm. Now, there's a few different notations I need to define in this estimator here. So this rho, so that's your distance function. That's your distance function between the simulated sum of statistics and the observed ones. So this k here is a weighting function. So this is actually very similar to what you would see in kernel density estimation. So the idea of the weighting function is to give a high weight when your simulated sum of statistic is close to there. So if your rho is small, then you want to give a higher weight to that simulation. Now, this kernel weighting function depends on this bandwidth parameter, and in the context of ABC, they call this the ABC tolerance. Okay, so if we think about the non-parametric perspective of ABC, then the choice of the epsilon is going to be a trade-off between the bias and the variance. So if we take our epsilon small, we're going to be reducing the bias, which is good because then this term is going to be closer to this term. But then at the same time, we're going to be increasing the variance. And this is a bad thing because when we pass it into our Metropolis-Hastings ratio here, then that's going to be estimated with high variance, and this is going to reduce the efficiency of the MC-MC. So this would mean you have to run your Markov chain for longer. Okay, so that's essentially ABC, and it turns out that ABC is very useful in practice. So there's lots of different disciplines that actually use ABC. So it's clearly a very valuable method, but at the same time, it does have some limitations. Firstly, you need to choose all of these different tuning parameters. So we've got the epsilon, we've got the distance function, and we've got the kernel weighting function. And it turns out that the ABC approximation can be quite sensitive to the choice of in particular, to the choice of the epsilon and also the distance function. Now, there's been a little bit of research on, trying to come up with standard ways to select these tuning parameters, but in the end, it's going to be very problem specific. So for each new problem, you're going to have to retune those parameters. Now, the other issue with ABC is that it doesn't scale particularly well to the dimension of the summary statistic. Okay, so in this talk, we're going to try and think about approaches that can sort of help us overcome these limitations to an extent. Okay, so I just wanted to talk about a motivating application for which ABC may not perform particularly well. So the application here is a stochastic model in collective cell spreading, and collective cell spreading has applications in wound healing and also skin cancer growth. So the model that we're going to focus on is the one from this paper here, and it's basically you've got cells moving around on a lattice, and your simulation model is a discrete time process. Okay, so for each discrete time step tau, we're going to give each cell a chance to move to a neighbouring location with a probability given by PM. And also during that same time step, we're going to give each cell a chance to give birth to another cell, and we're going to put that at a neighbouring location as well. Okay, so this is called the motility parameter, and this is called the proliferation parameter. Okay, so this is an example of a simulation from the model with these parameter values here. So you can see that you've got cells moving around on a lattice. In general, we've got cells kind of diffusing this direction. And if you look closely enough, then every now and again you might see a new cell pop up. Okay, so because the proliferation parameter is so small, you don't really get that many new cells, but there is actually some new cells popping up in here. Okay, so we're going to treat that simulated data set on the previous slide as the observed data set, and we're going to try to see if we can approximate the posterior distribution of these two parameters given that data set. Now, unfortunately, this particular model, it doesn't have a tractable likelihood function, but you've seen from the previous slides that it's very easy to simulate data from the model. Okay, so this is a very good candidate for a simulation-based approach. Now, the observed data here is basically a whole sequence of binary matrices, where if you've got a 1, it tells you that a cell is going to be present at that particular location. If it's a 0, it means that the cell is not present at that particular location at that point in time. Okay, so if we're going to do ABC, we need to come up with some kind of summarization of the data. So here what we did was we looked at the Hamming distance between these adjacent binary matrices. So this is basically just looking at the number of locations in those two binary matrices that are different. Okay, so this should give us some information about the motility parameter. And secondly, we looked at the total number of cells at the end of the experiment. So this should be informative about the proliferation parameter. So in total, we've got something like 144 images or 145 images or something. So if you add up all of these summary statistics, we've actually got 145 summary statistics. So this is quite high dimensional, and ABC is probably not going to be well suited to this dimension of the summary statistic. Okay, so as we've seen, the ABC is basically a non-parametric procedure. Okay, so we're going to see what kind of progress that we can make by, instead of making a non-parametric assumption on the summary statistic likelihood, we're going to make a parametric assumption. And the one that we're going to use is something called the synthetic likelihood, which was originally developed by Simon Wood in this Nature paper here. And effectively what the synthetic likelihood does is it makes a multivariate normal assumption about the model summary statistic. Okay, so we effectively approximate this intractable summary statistic likelihood with this multivariate normal density over here, where we actually allow the mean vector and the covariance matrix to depend on the parameter of interest. Okay, so you're probably thinking that this is a pretty strong assumption, and it kind of is, but at the same time, there might be a few different reasons why we could justify the normality assumption. Okay, so firstly, we might think that the summary statistics are sums of data points, in which case we've got the central limit theorem coming in. Secondly, we can apply transformations to the summaries in order to try to improve the normality. So, for example, we might have a positive summary statistic, in which case we could do, for example, log transformation. And thirdly, there's this other approach for coming up with summary statistics in ABC, and this is called indirect inference. Now, what you do in indirect inference is you have this auxiliary model, which has a tractable likelihood function. You fit this auxiliary model to the observed data, and the parameter estimates of that auxiliary model become your summary statistics for ABC. Now, under mild conditions, these summary statistics are actually asymptotically normal as well. But probably one of the most obvious reasons to choose the normality assumption is that the multivariate normal distribution is very tractable to deal with. So if you think about employing this within an MCMC algorithm, which you need to run for a very large number of iterations, you need something tractable to compute at each of those iterations. Okay, so we actually looked at a Bayesian version of the synthetic likelihood in this paper here, and we're going to refer to that as BSL. Okay, so here's how we go about estimating the synthetic likelihood. So again, for some proposed value of the parameter theta, we generate our n independent data sets. For each of those individual data sets, we compute the corresponding summary statistics. And then based on those simulations, we can compute the sample mean and also the sample covariance based on all of those simulations. So the issue with the synthetic likelihood is that we don't know what the relationship is between the mean vector and the covariance matrix and also the parameter of interest. But we can, of course, estimate those via simulation. So we obtain the sample mean and the sample covariance matrix, and we plug this straight into the multivariate normal density, and this becomes the approximate likelihood that we put into the MCMC algorithm. Now you can see that in comparison to ABC, we've only got one tuning parameter now, which is the number of simulations that we take at each iteration of the MCMC. Now, even if we use an unbiased estimate of the mean and the covariance, once we substitute that into the multivariate normal density, this overall density estimator here is not going to be unbiased for the ideal synthetic likelihood. So if we think about the pseudo-marginal MCMC literature, from a theoretical perspective, then the target distribution that you would get from this BSL procedure should depend on the number of simulations, because this is not an unbiased estimator of this quantity here. But we've actually found in a lot of different applications that there doesn't seem to be a lot of sensitivity to this tuning parameter. So it doesn't seem to matter how we choose the number of simulations. The approximation that we get at the end seems to be quite similar. But of course, the choice of n is going to affect the computational efficiency, and I'll talk about that a little bit later as well. Okay, so in order to try to gain some insight into how BSL compares to ABC as we increase the dimension, one of my collaborators, Anthony Lee, came up with this toy example. So here the likelihood function is given by this, where we've got a known covariance matrix and an unknown theta. And of course we can arbitrarily increase the dimension of this by increasing the dimension of the y and the theta. Now for ABC we're going to choose this Gaussian kernel over here. Now it turns out that for this particular example, if we choose the ABC tolerance as 1 over the number of simulations, we can actually get a correspondence between the ABC, so the likelihood estimated via ABC, and also the likelihood estimated via BSL. Okay, so we're going to get the same approximate posterior because we effectively have the same likelihood. Now, the two approaches differ in the way that these two quantities are actually estimated. Okay, so what we did is we did some theory by looking at the relative variance of these two different estimators. And what we found is that when the dimension of summary statistic is 1, then the ABC was more efficient than the BSL. When the dimension of the summary statistic was 2, then they had the same computational efficiency. But we noticed that as you increase the dimension of the summary statistic beyond 2, then the BSL becomes much more efficient relative to ABC. Now, of course, this is only a toy example, and furthermore, we fixed this covariance matrix, but we know in the synthetic likelihood that we actually have to estimate that covariance matrix. So we're interested to see, what is the computational efficiency gains also in real examples. Okay, so we implemented the BSL on this cell biology example. Okay, so firstly, we're looking at, well, how sensitive is the approximation to the number of simulations that we take per iteration? Okay, so we actually found that we get very similar approximations. And we found this to be the case for lots of different examples. Now, it just seems that it doesn't seem to matter how much, what value you choose for the number of simulations. You seem to get, approximately the same approximation coming out. And we can also see that there's kind of a range of values for n for which you get, a relatively similar efficiency. Okay, so if we increase the number of model simulations, then we're going to estimate the likelihood more accurately or more precisely, which means that the acceptance rate in your MCMC is going to go up. Okay, so there's a large computational effort per iteration, but you don't necessarily have to run your MCMC for a large number of iterations. On the converse, if the number of simulations is small, then the computational effort per iteration is smaller, but of course we're increasing the variance of the estimator, which is going to lead to a lower acceptance rate in your MCMC. So basically we can choose the number of simulations in order to maximise the computational efficiency. Okay, so now we did some comparisons with ABC. Now, of course, one way to overcome the dimensionality problem of ABC is to reduce the size of the data set. Okay, so the first approximation that we considered was, instead of looking at 144 images, just look at 3 images and see what happens. And so the posteriors for those ones are given in black here. And then we also looked at ABC using all of the images, which is the pink one. So you can see as we use all of the images, we're actually able to gain much more information about the motility parameter. So it makes sense to try to analyse more of these images. But when we look over here, we actually get a worse approximation using all of the images for the proliferation parameter. Okay, so this is actually the curse of dimensionality of ABC coming in here. So even though we've got more information in our summaries, we've increased the dimension and we actually end up with a worse approximation. In contrast, if we look at the BSL approximation, the BSL approach seems to deal pretty well with the high dimensional summary statistic. And we can see that the results also tend to agree with ABC also applying something called a regression adjustment. Okay, so we found that the synthetic likelihood approach tends to work quite well in lots of different examples, and there's also a whole bunch of other papers out there in the applied literature which also apply the synthetic likelihood successfully, but at the same time it does have some limitations. Now obviously we need the distributions of the summaries to be roughly normal, okay, so that's one of the limitations. Secondly, if our summary statistic is high dimensional, we still need to do lots of model simulations. So if we think about going back to this cell biology example, for every iteration of the MCMC, we need to do roughly 5,000 simulations from the model. So if you think about applications for which the simulation takes for a second, even that's going to be too long. Okay, so we still need to do lots of model simulations. And finally, we're relying on MCMC, and typically you want to run your MCMC for quite a large number of iterations, and this only gets worse and worse as you increase the number of parameters. Okay, so we're going to try to address some of those limitations, and the first one, in order to try to bring down the number of model simulations that we have to do, is to apply shrinkage covariance estimation. Okay, so it turns out that estimating covariance matrices in high dimensions is actually quite difficult to do, because as you increase the dimension, the number of parameters in your covariance matrix actually gets very large. So it turns out that the sample covariance matrix is not a very good estimator of the population covariance matrix in high dimensions. It has high variance. Okay, so one way to try to bring down the variance is to apply shrinkage. Okay, so we actually considered a couple of different approaches in our work. We've considered the graphical lasso and also a shrinkage estimator due to this paper over here. But in the interest of time, I'm just going to be focusing mostly on this graphical lasso. Okay, so all you have to do to implement the shrinkage thing is that you estimate your covariance matrix via this shrinkage procedure, and then you put that estimated covariance matrix into the synthetic likelihood, and then you put your synthetic likelihood into an MCMC algorithm. So it's very straightforward to implement. Of course, the amount of shrinkage that you do is going to be a trade-off between the accuracy of the posterior relative to this BSL method compared to the computational efficiency. Now, of course, as we increase the amount of shrinkage, then we're going to reduce the number of simulations that we have to do, so we're going to be increasing the computational efficiency. But at the same time, our approximation is going to be moving away from this other approximation. And the amount that it moves away is going to depend on the problem itself. Okay, so now just a little bit more background about this graphical lasso approach. So the idea of the graphical lasso is to obtain a sparse estimate of the precision matrix, which is just the inverse of the covariance matrix. Now, in order to implement the graphical lasso, all you need to do is maximize this penalized log likelihood. So this is your standard kind of multivariate normal likelihood here, and then you've got your penalization term over here. Now, we've got this tuning parameter lambda, which controls the sparsity. So as we increase the value of the lambda, we're going to increase the amount of sparsity that your graphical lasso estimate is going to have. Now, because we've got this extra tuning parameter, we need to choose this in some kind of way. So what we did is we took some advice from the pseudo-marginal literature. Okay, so with pseudo-marginal MCMC, we're using some kind of approximate likelihood within an MCMC algorithm. And the advice from this literature is to obtain a standard deviation of your log likelihood estimated to be roughly 1.5. So for a given number of simulations that we want to do per iteration, we choose the lambda in order to bring down the standard deviation of this estimated log synthetic likelihood to be roughly 1.5. Okay, so here's some results that we get when we apply this graphical lasso procedure into the BSL approximation for the cell biology application. So you can see that in this particular example, for a variety of different lambda values, we're actually still getting a pretty good approximation. Now, this is probably the best results, obviously, because I want to include it in this talk. I want to make it look really impressive. But, this is sort of the best results that we've got with this approach. And the reason why the results are so good is because I think there's a lot of potential sparsity in this application. And so this estimator is really taking advantage of that sparsity. Okay, so we're getting some pretty good approximations here. And we can see that, so we got some effective sample sizes down here divided by the computational effort. So you can see that we're increasing the computational efficiency relative to the BSL. And also our procedure for choosing this lambda has seemed to be pretty successful, because we've actually managed to maintain a similar acceptance rate as we change the number of simulations. Okay, so that was an approach to reduce the number of model simulations that we have to do in this MCMC BSL procedure, but we're still relying on MCMC. Okay, so it means that we're going to have to do still a very large number of model simulations. Now, in order to massively bring down the number of model simulations that we have to do, we came up with a variational Bayes approach for synthetic likelihood, and we found that through this approach, we're able to bring down the number of model simulations that we have to do by orders of magnitude. So it really is a lot faster. But at the same time, we need to make a multivariate normal assumption about the posterior. Okay, so if your approximate posterior really is close to multivariate normal, then obviously the variational Bayes is going to give you a very good approximation. But if that's not the case, then the VB approach will tend to give a pretty crude approximation. Okay, so in this paper here, we just developed the standard variational Bayes approach for synthetic likelihood, and then we extended the methods in this paper to deal with much higher dimensional problems. Okay, so when our summary statistic was high dimension, we considered shrinkage estimators of the covariance matrix. And for high dimensional parameters, then we considered a factor analysis representation of the posterior covariance. And through this factor analysis representation, we're actually able to massively reduce the number of variational parameters that we have in our VB optimization procedure. Okay, so we applied this variational Bayes approach to the cell biology application. Okay, so the black one here is just the standard MCMC BSL. The red one is just the standard variational Bayes synthetic likelihood, and the green one is VBSL with a shrinkage estimator for the covariance matrix. Okay, so because the posteriors are roughly normal, we find that the variational Bayes approach does give a pretty good approximation to the posterior. And we also found that the VB approach was less sensitive to the noise in the estimate of the log synthetic likelihood. So we found with MCMC that we have to do 5,000 simulations per estimate of the synthetic likelihood. But for variational Bayes, we found that we only had to do roughly 1,000. And then if we apply shrinkage on top of that, we only had to do 300 simulations per estimate of the synthetic likelihood. Okay, so per estimate, we've managed to bring down the number of simulations that we have to do. But furthermore, with variational Bayes, you don't have to run it for many iterations. Okay, so after about 50 iterations, you've basically converged to the best that you're going to do. Okay, so this is in comparison to MCMC, for which you might want to run it for tens of thousands of iterations. Okay, so we just looked at shrinkage estimators of covariance matrices and also variational Bayes approaches for trying to massively reduce the number of model simulations that you have to do. Now, the final drawback that we're going to try to address is the multivariate normal assumption of the summary statistics. So we're interested in a couple of different things here. We're interested in how robust this BSL procedure is to the lack of normality. And furthermore, we're proposing a more robust version of BSL based on a semi-parametric estimator. Now, the semi-parametric estimator that we're using is something called a Gaussian copula. Now, with a copula model, you're allowed to model the marginals separately from how you model the dependent structure. Now, the simplest type of copula model that you can have is something called a Gaussian copula model. Okay, so firstly, we need to construct estimates for the marginal densities of our summary statistics. So here we're using kernel density estimators. Now these are only in one dimension, so kernel estimates do tend to work quite well in one dimension. And we're also going to be adaptively determining this bandwidth parameter here. Okay, so we don't need to add any additional tuning parameters into the procedure. Okay, so we've got our kernel density estimates for the marginals. Then we can apply the CDF of that KDE in order to transform these samples. So after you do this transformation, then these values here should be roughly uniform, 0.1. And then you pass these values through the quantile function of the standard normal distribution, and then after that transformation, these samples should be roughly standard normal. Okay, so that's the marginal distributions. Now to try to model the dependent structure, we're going to be using this Gaussian copula. Now this thing here is the probability density function for the Gaussian copula, and it's only got a single parameter in here, which is the correlation matrix here. Now one way to estimate this correlation matrix is just to look at the sample correlation of these eta values over here. Now, in order to add a little bit more robustness to our procedure, we didn't estimate the correlation matrix that way. We actually used this non-parametric Gaussian rank correlation here. Okay, so after you've estimated this correlation matrix, then the overall semi-parametric estimator of our summary statistic likelihood is given by this expression over here. Okay, so there for all of the marginal statistics, and this is trying to account for the dependent structure between those summaries. Okay, so to try to investigate the robustness of this procedure, we looked at a few different examples. So we're going to start with this really simple MA2 time series example, where the observations evolve according to this equation here. Now, obviously, the joint distribution of all of these data points is going to be multivariate normal, where the variances are given by this expression. And we've also got a significant lag 1 and lag 2 order covariances, but all of the other covariances are equal to 0. Okay, so here we're not doing any summarization of the data, so we're going to take all of our data as our summary statistic. Okay, so this example is not particularly useful at the moment because our model for the data is actually a multivariate normal distribution. So of course the synthetic likelihood approach is going to work well. Okay, so what we did was we applied a transformation to each of the marginals. So we applied this transformation here. And the transformation depends on two parameters. We've got this epsilon, so that's not the ABC tolerance, by the way. So this is a parameter that controls the skewness of the transformation, and the delta is a parameter that controls the kurtosis. Now, when the epsilon is 0 and the delta is 1, then this is no transformation. As we increase the epsilon, we get some skewness, and then as we change the delta, we get kurtosis as well. So by modifying these two parameters, we can get some really interesting shapes for these univariate distributions. Okay, so these are some results that we get for different combinations of the epsilon and the delta. Okay, so of course when our epsilon is 0 and our delta is 1, then this is no transformation, so obviously the synthetic likelihood does well, of course. Our semi-parametric procedure still does well, and we're also comparing with this other approach called the extended empirical saddle point approach. So this is another approach to try to robustify the synthetic likelihood procedure. And by the way, this is still work in progress, so these aren't really the final results, but this is what we've got so far. Okay, so let's see what happens when we modify the epsilon and the delta. So we can see that when we've got heavy skewness in the marginals, then the synthetic likelihood is starting to move away from the true posterior. The semi-parametric approach still seems to work reasonably well, and unfortunately this saddle point approximation doesn't seem to be offering much robustness. Now for some different combinations of epsilon and delta, so again we find similar results here, that the semi-parametric approach still seems to be working reasonably well. So in this particular case, the saddle point does seem to help a little bit, but down here it doesn't seem to help very much, whereas the semi-parametric approach seems to be working pretty well. Now, we would kind of expect the semi-parametric approach to work well here because the dependent structure of, after you do the transformation, the dependent structure is multivariate normal. So in a sense, the semi-parametric approach is making the right approximation for this example, except for the marginal distributions, which we assume that we don't know. So therefore, we'd like to see how the method performs on some different applications as well. So I'm just going to go through a few more examples here. So I'm not going to tell you about the details of the models. I'm just going to describe how many parameters we have and also the dimension of the summary statistic. Okay, so for this queuing example, we've got 3 parameters and we've got 50 summary statistics, and these are what the marginal distributions of the summaries look like. And so you can see that they're very much not normally distributed, so it'll be interesting to see how the synthetic likelihood approach goes in this example. Okay, so these are some marginal posterior distributions that we get. So we can see that with the semi-parametric approach, we seem to get much more precise posterior distributions. So it's a bit hard to compare the methods without having the true posterior, but it seems that, given that the semi-parametric approach seems to be giving much more precise estimates of the parameters, it's probably doing a bit better in dealing with the non-normality of the summary statistics. Okay, so finally we're going to look at this example which is going to really push the boundaries of the semi-parametric procedure. Okay, so in this example, we got 4 parameters and we got 12 summary statistics. Okay, so what I did was take a particular parameter value of this model, generate lots of simulations from the model conditional on that parameter, and then look at the bivariate scatter plots of these summary statistics. So you can see that you've got some very strange dependent structures between these summaries. So even the semi-parametric approach isn't going to be flexible enough to handle this kind of distribution here. And these are some results that we get. Now, because we've only got 12 summary statistics here, we're going to take ABC as the gold standard. So as long as you throw enough computation at the ABC, it's going to give you a pretty good approximation. Okay, so we can see that the BSL approximation is not particularly close to the ABC one. And also the semi-parametric approach doesn't seem to really help that much. Perhaps it's maybe being a little bit closer to the ABC approximation, but overall it's not giving a very good approximation. Okay, so this is providing some motivation for people to develop even more robust approaches for synthetic likelihood. Okay, so that's basically all I wanted to say. Just finish up with a few things. So one thing is that we're creating this package BSL. So a lot of the methodology that I spoke about today is implemented in this R package, and we're going to continue to evolve this package over time. And finally, some future work. Okay, so we've actually found that the synthetic likelihood can be robust in certain situations to non-normality of the summary statistics. So it'd be nice to have some theory behind, when we can expect the synthetic likelihood to be robust to non-normality of the summary statistics. So that's one thing. The second thing is to try to come up with even more robust approaches to BSL, even comparing to the semi-parametric approach here. We also want to try to extend to more flexible variational distributions, because at the moment in our synthetic likelihood procedures, we're only coming up with a multivariate normal approximation of the posterior. So we'd like to have some more flexible variational distributions there. And finally, we'd like to explore some of the asymptotic properties of synthetic likelihood. So what happens to the synthetic likelihood procedure as the number of observations gets larger and larger? And so these are some of the papers that we've written on this topic, or all the papers that we've written on this topic, and also just including the original synthetic likelihood procedure down here. That's all I wanted to say. Thanks very much.
Sensitivity of your data, and as you mentioned, how about mixture distribution or heavier tail case? The true likelihood is heavier tail, as you are trying to apply lighter synthetic likelihood.
Okay, so do you mean using a mixture of multivariate normals as opposed to just a single multivariate normal? Yeah, so this could be a useful approach as well. So I guess one limitation with that might be that you need to estimate the parameters of that mixture of multivariate normals. So for each iteration in your MCMC, you'd have to run like an EM algorithm or something in order to estimate the parameters. So because we're putting this inside an MCMC procedure that we're calling a large number of times, we need something that's sort of quite tractable. So the mixture of normals could be a good idea, but it might add also a little bit to the computation as well.
The